So I will give you a little bit information about the Qatar Computing Research Institute, who we are, what we do. Then it's a somewhat personal journey to speech translation, so I'm looking back a little bit. I give some examples of speech translation systems, and also actually towards the end what we work on, what others have worked on, and also then a little bit about what actually are some of the challenges in speech translation. So about the Qatar Computing Research Institute. So this is an institute which was established in 5 years ago in 2010 by the Qatar Foundation. So Qatar Foundation is essentially this organization who builds educational and research development capacity. So there is the Hamad bin Khalifa University, there is also a school, Qatar Academy Middle School, high school, there is the Science and Technology Park for technology transfer. And there are these several research institutes, so we are one of three. There's also one for energy environment, one for computational biology. And this started, many years ago, and it's growing. We are right now more than 100 people, so this is one of our events. Actually, I was traveling at the time, so I'm unfortunately not in this nice picture. What is very important is that we are actually very multinational. So in our research institute, we have more than 30 nationalities. I think in the Arabic language group, we have, I think, 11 nationalities. And it's a rich mix of academia and also people came from industry, from companies, and so on. So it's a very, very inspiring environment. So the vision and mission here to be a global leader of computing research in identified areas. So we cannot do everything, so we need to focus on some. And what's important, to impact the lives of the people. And this then also comes back. So enhancing the quality of life of citizens, stands high up there. So it's not even primarily about, cranking out the next publication, the next paper, and so on, but actually, do we generate some impact? So this is a kind of diagram our research director, Dr. Ahmed, had drawn at some point. So overall, we have 6 research groups in QCRI, Qatar Computing Research Institute. There is the data analytics and distributed systems. Last year, cybersecurity was added because it was identified as a national priority in the entire country, next to water security, energy security, and so on. And then on top of this, we have 3 more application-oriented areas. The Arabic language technology is one of these, but also social computing, where we do a lot of work in the humanitarian humanitarian health and disaster space. And then there is the computational science and engineering, where colleagues work, for example, on medical problems, biomedical problems, obesity, and so on, diabetes. In the language group, so one of our research focus areas is enabling information flow and communication across language barriers. Right, so this is obviously machine translation, but then also including the speech recognition, which we do in its own right, but then also as a component of the speech translation pipeline. We also put under this actually optical character recognition because it has very similar technologies. And so recently we developed an OCR system, especially for historic Arabic documents in collaboration with the National Library, that we can give access to these interesting historic documents. Another area is information extraction and question answering. Again, trying to have some impact. So, for example, we collaborate with one of the portals in Qatar, with Qatar Living, where people can ask questions and so on, where the people answer. And so we develop technologies, for example, to give a better search. What other answers have been given to similar questions in the past that they rank high up? We have done some work on e-learning. So just to mention, we have developed an Arabic e-book reader, which has been tested in some of the schools in Qatar, and where we are in discussion with some of the content providers, school book providers, that they adopt the readers and this is very nice, a very nice product. And then enriching Arabic digital content. So this is not so much research-oriented, it's really supporting, for example, QCRI sponsored the translation of Wikipedia articles, and right now we have a project to translate medical content from the Mayo Clinic, that it becomes accessible to the entire population. So this is just as an overview where I come from, what we do at QCRI. So let's start more on the speech translation. And as I mentioned, I give it as a kind of personal journey through this. So this is where I have been over, since 1995 when I actually started to work at the University of Aachen. So I was for 5 years at the University of Aachen, a couple of months at the University of Karlsruhe, and then I moved over to CMU. So this short period in between was because Professor Alex Vogel, who had invited me to come to CMU, is also professor at the University of Karlsruhe. So there's always collaboration going on, and he said, first come a couple of months here, let you know people face to face because we collaborate on one project, which was very good. And then I spent about 10 years at CMU, and then I decided why not be a little bit more adventurous, go to some place which is very different from the places I had been before, and I have to say I didn't regret it. So it has been very exciting 4 years since I joined QCRI. And of course, 4 years ago it was still very small, so in the Arabic language technologies team at that time it was one scientist, one software engineer, and by now we are about 20. But let's look at this from a slightly different angle. So these are some of the projects I have been directly involved in, or at least in, peripherally involved in. And so the first project was the WebMobility project, which was a very big project in Germany at the time. It was running overall for 8 years. We had about 100 people in there. So everyone who was not in the project was mad as the science minister, because this project sucked up all the money in language technologies for 8 years, right? So there was no money left for any other projects. So not all people were happy. UTrans project was a project with Spanish colleagues, and then other projects, some of these big data funded projects like Tiled, Scale, Bold, which all had actually Arabic to English translation, also Chinese to English translation. And so I color-coded some of these projects, some were in Europe, some were in the US, and I mean, even those in the US had always international collaborators. So for example, Aachen and the University of Edinburgh were involved in the Gale and project, Hong Kong University of Science and Technology. But now when we look at what kind of techniques have been used in this, and what were the goals in this project, so we see that initially all the speech translation projects were essentially very limited domain translation. So for example, in WebMobility it was about arranging a meeting, a time and a place to meet. So these were these simple dialogues, they were recorded in mock-up telephone calls and so on. So it was small vocabulary and fairly simple, short sentences and so on. Similarly with the UTrans, this was also travel domain, Nesprey was travel domain, Babylon was more for the US, which was low resource languages, was already opening up a little bit. But we see that initially it was this very limited, and only later then actually people were more bold and techniques had developed far enough that we could move into larger vocabulary, both in speech recognition but also in machine translation. And so we see these data projects, which are now mostly unlimited or large vocabulary unlimited or a wide range of limits and so on. For example, news translations. There were still once in a while the more limited domain like the translate, which was force protection dialogues. And yet another view on this is what kind of techniques have been used. So we started in 1996 with the so-called statistical machine translation, and especially the phrase-based statistical machine translation. So in the history of machine translation, there have been different approaches. Initially, it was more from a linguistic point of view, analyzing the structure of a sentence. As we learned it in school, there's a noun, there's a verb, and so on, there's a structure. And when I go into another language, I have to shop around things a little bit. In English, I have the verb in second position. In German, we often have it at the final position, but then auxiliary verb and all of this, right? And so there was this grammatic-based approach. Then there was also the interlingual-based approach, which was essentially, can we map the meaning of a sentence into an essentially language-independent representation and generate from this representation into whatever language you want. So the advantage is that I can have n analysis components and generation components. They all go through the same hub, which is more efficient in a way than having these grammar-based, transfer-based translations, which has to have some component for each language pair. So it's n times n minus square translation components. The statistical translation approach was pioneered at IBM some 25 years ago in Yorkton Heights. And they were coming from the speech recognition part. So statistical machine translation is essentially mimicking for translation what has been done for speech recognition very successfully. And so in Germany and probably in Europe, we were the first adopters of this translation approach under the Webmobile. So we came in halfway into the Webmobile project with the statistical approach. We still see some of the interlingua-based approaches. So at CLU, colleagues were still working on the interlingua, but then essentially interlingua was fading out. The more we moved towards large vocabulary, the less viable the interlingua-based approach became, because it's just too cumbersome to decide, okay, this is a table, right? So this is a table, this is a concept. You have to have an entry in your lexicon for this, I have to have an entry for this. When we make the component, we need to know something about plural, about gender, and so on. So the entire community moved now towards especially the phrase-based translation, and in more recent years there have been some other flavors under the statistical translation approach, which now pull in again more of the linguistic information, which initially, just for getting off the ground, we essentially had neglected. IBM just did word-to-word mapping. Then we did phrase-to-phrase mapping, and now people also use tree-to-tree mapping, string-to-tree mapping, and so on. So the techniques have become richer, and more information can be incorporated into the statistical machine translation approaches. So let me just display this. Okay, so statistical machine translation, we rely on the human translator, right? So the human translator has already translated. The largest corpora which we actually train on are from the United Nations, because documents have to be translated into the official languages. So we have something like 80 million words of Arabic, English, Arabic corpus by now. And so when we move down, we train from this public corpus a translation model, but we also train a language model, because it essentially tells us what is the good type of language. And then we develop a program which can take a new sentence, takes these models to generate new target sentences. And so the advantage is, if we have the data, we can actually build these translation models fairly quickly for the language pair. Of course, the downside is we need these product corpora, and they are often not available for many languages, for dialects, and so on. They are not available. So the idea developed by IBM is that we use these multi-channel models. So essentially, their metaphor was someone is speaking in English, sends it through a channel, through a transmission channel. It gets garbled in the channel, some noise is added. What comes out on the other side sounds now like French. But we need to recover what was originally spoken in English. And so the underlying mathematic here is that we want to find the English sentence, given a French sentence, which maximizes this probability, any English sentence given a French sentence. And using this, we can actually factor this into the language model part and the translation model part. So we model the source and we model the channel. And the source is what we want to recover, and the channel is what disturbs the signal in the first place. And when we have these models, then what we do, given the new sentence coming in, which now I structure as a kind of lattice here. So this is my sentence which I want to translate. I use here German. So now I can harvest what I have learned from these parallel corpora where I have extracted translation pairs. And I can match now all the input phrases within this sentence with translations which I have found. Okay? So I build now this entire lattice, and then in the second step, I need to find the best path through this lattice. This is now the decoding part. So I have the translations applied to it, and now I need to find the best path. Of course, there are many paths here in real life. You know, it would be much higher. You know, we typically see 10 to the power of 20 paths in the lattices. So of course we cannot explore all. So you need to do the dynamic programming and so on. So I just give an example. And what makes it actually harder is that we need to consider reordering. So it's essentially computationally equivalent to the traveling salesman problem. You know, factorial to the number of words times the fan out in these nodes. So let's say we have already translated the first two words into this I will come. So this is one of many alternatives. So now I can jump ahead. So I don't translate the next word. I can jump ahead, leaving a gap, and I store this information here in a coverage vector. So I have translated 1 and 2, a gap here, and then the other two words. So I expand it, and then I have to jump back to fill the gap so I can do the reordering in the translation. And if this has now the highest probability, then I output this as a final translation. So let's go back to some of the projects along the line which I have seen shown before. So the Webmobbing project in the 90s was, as I mentioned, a large speech translation project, and actually many components were included in this project. So it was not just one pipeline. So we see here, down here, so it's in German, unfortunately, but we have different speech recognizers for different languages. Then we have prosody analysis on top of this. And then all the other part is actually different kinds of translation. So we see here semantic deep analysis, so this is the grammar-based, transfer-based translation. Then here we see two direct parsers. So all of this up here belongs to the transfer-based approach. And then here we see the statistical translation and the example-based translation, which go directly, and then we have the synthesis. And then there was also a lot of interesting research. Actually, in the end evaluation, what Professor Walz at the time called the quick and dirty was actually the best translation path overall. So the statistical approach, even though it came in late, actually could catch up with the other translation approaches and even surpass them and generate overall better translation. So there were a number of highlights. Some I mentioned already. System combination for translation engines was tried at the time it didn't work. These days, actually, we gain a lot from system combination. And this may even be on the level that we do on the same input, different morphological segmentation for Arabic using different levels of segmentation, translating them, and then recombining the results. So even with the same output, we can actually do multi-engine translation just by having different pipelines which we go. If we have now different translation systems from other groups and so on, we can gain even more. Prosodic annotation, I really loved at the time what the group in Erlangen, especially in Erlangen, was doing on prosody annotation. So they could identify 5 segment boundaries, which we actually used then in the translation as substitutes for punctuation, which were not delivered by the speech recognition. Or that something was recognized as a question, which is important to in the translation. So many of the problems which were identified at that time and were tackled, sometimes successfully, sometimes not successfully, in a way still remain today. Right? So you still have the problems when something comes in from a speech recognizer up. The recognizer does not do any true casing. Where do we fit in the true casing? Because in language, when I put the text out, I may need spacing. I may need punctuation marks. Where do I segment the input that I can cut it into sentence-like elements and so on? So many of the things actually go on and on and on and have not found a solution where people say, okay, let's start this. Another project which I have mentioned and I listed here was the Nesprey Project. So this was actually an interlingua-based approach with many partners. And the interesting part here was people always claim statistical translation actually is fine, but if you don't have this huge product program, it doesn't work. So in this project, or in this experiment, we actually could show that even with very limited resources, I mean, we talk here about a couple of thousand sentences as parallel corpus. This is tiny by any standards. You know, it's not the 1 million sentences. So we actually, and of course it's very limited vocabulary, you know, 1,000 words, 400 of which are seen only once in the corpus. And then we did both automatic evaluation, but more important is the human evaluation. So we were comparing the interlingual-based translation, the SMT translation, and both text input and speech input. Speech, of course, gives lower scores, but when we just evaluate it as good translation, okay translation, bad translation, and combine this into a score, we see that on both conditions, actually the statistical approach outperformed the interlingual-based approach, where people have been working, you know, for an entire year to build the interlingual structure. So overall, the translation for both systems were pretty bad. Right? If you have only 1,000 words, you know, it hardly is sufficient to communicate even in a limited domain. But it was important to show that, you know, this is a myth, that you need already, you know, millions of sentences to train a statistical translation system. Yes, you need vocabulary coverage, but given these limited resources, the statistical approach actually can perform quite well. So I mentioned that the limited domain translations, they often were using the travel domain So how can we build a translation system when we are actually on the run? So one option is, you know, we just carry the equipment which we need to do the heavy lifting for the statistical approach. Of course, this is not very comfortable. So another approach is that we use the front end, these days the smartphone, at that time, you know, the iPad and so on, and actually the heavy lifting of the speech recognition and translation is done on the translation server in the back end. This requires that you have connectivity. Can you actually build a speech translation system which runs on your device? And this is now work which was done, you know, nearly 10 years ago, where we didn't have the smartphones, but we had you know, systems like this, which had very limited memory and no floating point processing and so on. So how do you develop now a probabilistic system, you know, which calculates with probabilities and so on, and which requires fairly large memory when you have such a device. And so we built an architecture which reused some of the resources. So if I want to translate, let's say, from English to Arabic and Arabic to English, they essentially use the same phrase table. It's different probabilities in both directions, but it's essentially the same inventory. So you can reuse the phrase table and structure in both sides. Similarly, the speech recognition and the speech synthesis can reuse some of the resources. So we could build a system based on fairly compact data structures and reusing some of the resources. Right? So we had only 64 megabytes available for dynamic memory. So the models were actually stored on the flash drive, and we did this without floating point processing. Right? So we had compact data structures, integer-only computing, efficient decoding, and minimal computation on the device. But just about the data structure, just as an example. So instead of storing actually the phrase table, the corpus itself has all the information and takes less space. So this is even for a standard language model. When you go from a trigram language model to a four-gram language model, it's actually more data than the original corpus. So we have been working on the so-called suffix array representation. So you store the entire corpus, and then you have just pointers into the corpus where you found the phrase, and then an additional table which gives the pairing, right? And with this data structure, we could store essentially 5 million entry phrase table on the disk. Right? So in the end, let me switch directly to here. So in the end, on one device, we could actually run multiple language pairs, you know, on the device, speech recognition, translation, and the speech synthesis. This is a vocabulary of about 10,000 words. And this was travel domain, medical domain, in some languages also came out of the Untitled Project, the post-projection. And so actually the student who worked on the decoder for this system then became involved in the company, typical company, which was founded by Professor Alex Weibel. They released the product, and this is the company which was bought by Facebook, right? And now they are doing the translation at Facebook. So going back to this picture, so we have the limited towards the unlimited. We have seen the limited domain and so on. So one of the projects which was tackling the unlimited was the T-System project in Europe. Through our collaboration with Karlsruhe, we were involved in this. And so the interesting part is, in Europe with all the languages, so there is this trendy language parallel corpus, both in verbatim transcription. So if someone gives a talk, then they transcribe it verbatim, and later they edit it, and they release it then as a text edition. So it's actually interesting data, and this corpus has become quite famous, I would say, in the machine translation community. So all the WMT machine translation evaluations, which have been running now for many years, are based essentially on these Europal corpus. So let me see if, oops, did not just my, there I wanted to play the video. Now it's flashing. Okay, so while it's restarting here. So the video would just show one of these talks given in the European Parliament, and lady speaking, and you can see the subtitles. Okay, so I don't try to play this video. So a related project which we had at CMU under the acronym Stardust, lecture translator. So there we tried to do the real-time speech translation now for, let's say, people giving a lecture. So here we see Professor Alex Weibel while he's actually demonstrating the system. So we built it for English to Spanish, English to German, and actually with an intern who was working with me at CMU at the time, we also had a first English to Arabic version. And so these translations would come out in parallel. So this is the screen as it looked. So up here we see the speech recognition, there is no casing information, there is no punctuation, and then we have, unfortunately it's not very focused, the projector, then we have translation into Spanish, we have translation into German, and we have the translation into Arabic down there, and the quality also degrades as we go down. So Spanish, English to Spanish is reasonable. Again, this is from many years ago. In English we have this, in German we have this long-distance reorderings, and Arabic was built on very limited resources. So let me, how are we actually this time?
15 minutes.
Okay. So let me, okay, so these were just some of the examples of some of the projects I have been involved, what kind of challenges come up. Some are just engineering, how do you fit now the fairly large statistical models which you train onto a limited memory device, and others were more fundamental questions. And so I will come back to some of these here when I talk about the speech translation pipeline. So we get in some acoustic signal. So the first step is the speech recognition. Then on the outside we want to have, again, spoken. So we need to do the speech synthesis or text-to-speech, and then in between we have the translation, right? And so what researchers typically do is trying to decouple these things as much as possible. From a theoretical point of view, actually, you would forget about the language model which is used in speech recognition, right? When you just use the noisy channel model, so we would take away the language model from the speech recognizer, and the language model on the target side would have to, tunnel through the translation model and influence the speech recognition system. But this doesn't work. If you take away the language model, they are completely lost, right? So people essentially say, let me do the best I can do. I give you my first best output from the speech recognizer or from the translation, and then you take it from there. And of course, in a way, this is a little bit unsatisfactory, right? So people started to ask, how can we connect these different modules, and how can we optimize the end-to-end system, the entire pipeline, instead of optimizing each component individually? So when we look between speech recognition and machine translation, yes, typically we take the first best output, but could we do better when we take an best list, a 10 best list, 100 best, 1000 best list? Yeah, when we go to high ends, then it's more efficient to actually encode them in the lattice, what the speech recognizer is doing internally anyway. So can we take an entire lattice from the speech recognizer and feed it into the translation system? And then can we use actually the information from the speech recognizer to help the translation system? And then on the output side, should we just send the plain text, or should there be some annotations which even may tunnel through information from the speech recognition or from the property? What kind of speaker? Maybe we have here some speaker identification, male, female. Do we want to have now a male, female voice on the TDS? Or there was an emphasis on a particular word. Should we actually hand this over to have the emphasis also on the output side? So this then leads to an entire sequence, entire list of research topics. So the first one is this tight coupling between the recognition and the translation. So the lattice translation, but then also using the ASR features. The language model scores the recognizer has seen, the acoustic model scores has seen, or a combined confidence score on the speech recognition side. So should I prefer a path in the lattice where the recognizer tells me I have high confidence over where I have no confidence? I mentioned already the other one, segmentation, restoration of punctuation, disfluency detection. We all speak with arms and break in the middle of the word, all of these. How do we deal with this? Which you don't see in text translation. And our translation system is trained on text, right? So now we train a model and then try to apply to very different conditions. Then very important is this short latency translation when we want to use the system in, say, a situation like here. So if we have actually an automatic translation which would translate now what I speak into a foreign language as a human interpreter is doing it, with a short latency of maybe 10 seconds, a few words. And then the end-to-end optimization when we connect these components. So the lattice translation motivation is obviously clear. The recognizer actually has some models which are also limited. So what the recognizer considers to be the best sequence of words is not always the best he actually has seen. So it's not only not that he's making errors, but actually some of the errors are just based on not knowing what it was good and bad. So when we have now an entire lattice, then we can find paths which have a much lower word error than the first best, which is output by this recognizer. So can we now combine the information from the recognizer and from the translation system to find paths which actually have a lower word error rate? Or actually, could it be that there are some paths which are even worse but generate better translations? So there is no guarantee that the path with a lower word error rate from the recognizer actually gives the best translation. So these are kind of experiments which have been done. So then, of course, when you input an entire lattice into the machine translation system, then it becomes a little bit trickier. You don't want to translate a word twice, or an acoustic from the acoustic signal. You cannot cover the same input twice. So you need to take care what has been covered, what not has been covered, and so on. But this can all be done from a technical point of view. But then when you look at the results, right? So is there a general picture? There's none, actually, right? So I have seen things like, I reported here in IWSIT, which runs an evaluation, 2005, Wade came and said, oh, we have this tight coupling, we gained that much. Next year he came and he didn't mention it. I asked him, did you use it? Oh, it didn't help this year, right? So what worked last year may not work this year. Some people reported it works only on small lattices, others reported it works also on large lattices, right? Some said it works only for mid-range word error rate, others said it works only for low word error rates. Translation systems sometimes selected paths with lower word error rate, and sometimes it selected paths with higher word error rate. So looking over a number of papers, there was always, to one standpoint, there was also kind of opposing. So it's, I would say, one of the problems which has not been found a satisfactory solution. So people are not saying, I always win when I put in a lattice. So most of the time, actually, they are just taking the first best. So this is definitely an area which requires more word. Maybe with stronger models in the future, we get these problems. So right now, our models are still too weak, to select the few grains of gold, in this vast area of sand. So when you expand your lattice, recognizer lattice, then the number of bad paths grows much faster than the number of good paths. Punctuation recovery, different paths are possible. So do we first restore punctuation on the source side when it comes out of the recognizer? Do we restore it only after translation? Or actually is the translation system itself restoring the punctuation? And depending on which path I go, I train a translation model after removing all the punctuation on both sides, or after leaving them on both sides, or actually removing them on the source side, leaving them on the target side. And there again, people have reported different results. So one experiment which was done in our lab at CMU at the time gave best results when restoring the punctuation on the source side. So the recognizer does not generate punctuation, so we use a hidden event language model. We can restore, or other techniques, conditional random field, whatever you want to use. So you can restore punctuation on the source side, and the two bars are for text input and speech input. Speech is always worse. When we restore on the target side, it's a little bit worse. When we leave it up to the translation model by training on no punctuation source plus this punctuation target, it was worse. And when we use the manual correct punctuation, we are slightly better than actually, only slightly better, I should say, when restoring on the source side. Segmentation is always an issue. So the easiest thing is just to say when the speaker makes a pause, I cut it, right? In text translation, we always work on the sentence level. There's a full stop, the sentence is the end. This is what I train my model on, and this is what I operate on. This is not the condition when we have speech translation. So how do I segment? Boundaries is easy, but not very correct, right? It does not say much about the structure of the sentence, actually. So people also use language model information, they use prosodic features, and so on. As I said, in the Nesprey Project, a lot of interesting work was done to do the segmentation and so on. Later, I see that people often use just a simpler model. The long pauses, and at some point, if the segment becomes too long, I just cut it anyway. So, general picture here again is we know wrong segmentation periods. It's not entirely clear, how long, how short the segmentation should be. People have reported when I have longer segments, I get better results, which makes sense because all of the models need some history. The language model needs to look back for the decoder and so on. Other people have reported, actually even in our own lab, two different people have come up with different results. The one argued for shorter segments, the other one argued for longer segments, with slightly different techniques. Looking at the phrase table in the phrase-based translation system seems to help, so that we don't cut when we know actually our translation model has a long edge which will bridge over this segment part. What we have started to work on now is the low latency decade coding, so this is going towards the simultaneous interpretation by machine. So the considerations here are how much context do our models need? So we use a language model. In translation, it's typically, for large vocabulary, we typically use a 5-pound language model, which is longer than typically used in speech recognition. The phrase pair and standard settings, for example, the open source Moses toolkit, which is used widely in the community, the default setting is we collect up to 7 word phrases. So this is then a fairly long context. Word reordering, which I mentioned. Some languages you need to move the first word to the last word. Decoding complexity cannot cope with this at these times. So we restrict reordering window maybe to 4, 5, 6 words. So these are all essentially contexts which we need in the speech translation pipeline, which determines how much we have to train behind the actual speaker. So in decoding, then we take in one word at a time as it comes from the speech recognizer, and the speech recognizer can do this string decoding. It's easier, it's monotone processing. But then the output, we are not outputting one word at a time. The word can be translated into 2, 3 words anyway, or may not have translation, right? Maybe a part of a larger construction. So the output is now incremental in small chunks. So we trail behind the input, and then sometimes we catch up, and then we fall back again. Similar as the human interpreter actually does it. You know, he needs to have the concise information because he can commit to some output. So right now what we do in translation, and I have shown this before, we go in these two steps when we have an entire sentence. The first is we get all these translations, put them, generate these lattice, and then we have this first best path 30. When we do now the low latency, we have to interleave these two processes constantly, right? So not separate them. Then it looks more like this. So let's say we have already translated, you know, along this lattice, and a new word comes in here, right? So I have added this now. So in the next step now, I need to find all the phrase pairs which can incorporate this additional word. So it could be word-to-word translation, but also going back over the previous words and find longer phrases. So now I loop over these additional translations, which I may find here. You know, one is a word-to-word translation, one goes over 2 words. And then I can now open a new stack. So the stacks are here, how many words have been translated in the sentence. Not necessarily all from left to right. As I mentioned before, sometimes I need to leave a gap open and come back a bit later. So actually here I have listed some hypotheses, you know. Here I have translated the first 2 words, here I have translated 1 and 3, and here I have translated 3 and 4, and left a gap, right? And here I have already translated 3 words, here I have translated 4 words, which all actually cover the first 4 words. So now I have to take each of these partial translations and expand them over the edges which I have newly generated, which are here in blue. Right? And I can generate these essentially from each of these previous stacks within a certain window. Right? So I can now jump back and take one of these, leave a gap open, and translate now these ends, these words at the end. So now I get here the hypothesis, I will come, you, which translates 1, 3, and 5. And so I can go over this and expand all of these partial translations here, and I fill them into the appropriate stacks depending on how many words these hypotheses have now translated, all the way to where I have now the translation, I will tomorrow to you, right? Which again is not a very good translation at this point, but just to show how the procedure works. So let me summarize here. So speech translation, what we have seen, you know, by just looking back over some 20 years actually, how things have developed, what we have seen is that the advancement was from limited domain, small vocabulary, and so on, to large domain. So these days, you know, our speech recognizer has 1.2 million words in the dictionary. You know, not just 10,000 that we had 20 years ago. So domain limited is possible actually on handheld devices, and actually now with the smartphones, you know, they have lots of memory, lot of computing power. So you can have it on the device. Of course, the big companies, they want your data, right? So they offer it not that it runs on your device, unless in, you know, when you, like Google Maps, you can download it and then they delete it after 2 weeks. They actually want our data because this allows them to improve their services. Different translation approaches for speech translation. So we have seen there was the interlingua-based translation. I didn't talk much about the transfer-based translation systems. Interlingua-based, especially for dialogue systems, but in a way it has died out. Right? Maybe that is coming back. So people are now working on a specific approach to interlingua-based translation, right? So that you have a meaning representation, and then we need to train the model to map into this interlingua, and then from the interlingua out. So I'm not saying, you know, that these approaches are better or worse. You know, at some particular time, it just can make one approach work better with the resources, data resources, computing resources, with the mathematics that you have at hand. And there's constantly progress, both by having more data to train our models, but also by progress in the modeling and in the algorithmic part. I mentioned special speech translation problems. Many are still kind of unsatisfactory with no satisfactory solution. So let me just end with a couple of slides, what we currently have cooking at the Qatar Computing Research Institute. So let me introduce actually the team. So we have brought in quite a number of strong people. For example, Luis Marquez was just the general chair of this year's ICNLSP. Alessandro was the chair of ICNLSP last year, which we actually hosted in Doha. So this is one of the major conferences in the language processing field, not speech, but text processing. As you see, we have people obviously coming from many different countries. So we want to want to build systems which bridge the language barriers for news, for lectures. Maybe Khan Academy is an interesting example, and then eventually also meetings. We have presented our system to Shaika Mosa at the conference, and she was very interested and very sharp in her questions. She asked us. So this is a news page from Al Jazeera. So we collaborate with Al Jazeera. I mentioned, our director always asks, what is the impact? So it's not just the paper, it's actually developing systems which can be deployed. So we run a 24/7 service for Al Jazeera. They put something into a processing pipeline, which we automatically download. We generate subtitles for the videos and we upload it again. So it's not in real time, it's essentially processing overnight, and then when they put their videos into the archive, it's available. You can then also translate the page, the entire English of the page, re-render it and so on. But the interesting part is the subtitles. So again, it's blurred here, so we can generate the subtitling here. It works pretty well when you have the anchor speaker, the modern standard Arabic and so on. Our accuracy is 95% very often. When the reporter goes into the street, when you have the colloquial language, when you have the background noise, it doesn't work all that well. And so working on the dialects especially, is one of the high priorities now to do. And then of course we can also translate the subtitles. I do have a video maybe if people are interested later on in the topic. So I mentioned that we work with Al Jazeera. We have now started on phase 2, where we want to do the real-time processing, the low latency processing. That while it's broadcast, that within seconds we have generated the subscript and also the translation. From modern standard Arabic, you can train on hundreds of hours of data. For dialect, it looks very different, and we have already some discussion. There, finding even hours is already very difficult because this is not what's typically in the news. We have started to work on lecture translation, right? Where we actually make even recordings in local conferences in the interpreter booths, both original speaker and the interpreter get it transcribed to build a corpus for English, Arabic, English, similar to what was done for the Europower corpus. And for meeting translation, we have built first components, front end, back end, similar to the Skype translator. So some of you may have seen the announcement. I think it's out in Spanish and 1 or 2 other languages, so that you can actually communicate with other people's over a system which records what was spoken and translates into other languages or other practitioners. And most recently, we organized a kind of roundtable where we invited colleagues from the Citra Hospital, from the Hamad Corporate Hospital, from Y Cornell Medical School, and from the Translation Interpretation Institute. So actually, this poster was up in 2011, and I was there as a visiting researcher at UCI. It just struck me. Essentially it says, they did a study in the hospital, 450 patients. Some speak English, a few more Arabic, but then, it's Urdu, and it's Hindi, and it's Nepali. So I have been told at the workshop that right now, the highest population is actually from Nepal. So there are about, 400 or 500,000 Nepalis in Qatar right now. This is more than actually Qataris in Qatar. And so they have actually this problem, and Y Cornell started an interpreter education program, native speakers becoming interpreters in the medical area. And so our question was, can technology help? And we have invited the colleagues, to discuss what could be done together. Honestly, if I need to go to the doctor, I prefer that he speaks my language, or maybe English, but even there, it's not the everyday language which is spoken, right? Or I have a very good interpreter, right? But if this is not available, can actually technology help? And we have these situations. I remember an email when I was in Pittsburgh, which was sent to CMU. 200 refugees coming, one interpreter. Is there technology which can help? You know, they really wrote, is there technology which can help? So these situations are out there, and we as a community, we have failed for such a long time to actually deliver systems which can help in these systems reliably enough. Right? And these are critical situations. And we had over the summer with some intern projects, you know, collecting resources from different sources, from YouTube videos, from the dictionary and so on, because we need the resources, the data, the algorithms onto the system. So looking back at the journey, you know, I had covered a little bit where I came from and so on, but I think there is still a very long road ahead, especially when it's not just about the next publication, but really delivering systems, you know, from research institutes, maybe then from the companies, which actually help people in everyday life. Thank you.
Thank you very much.